it's a pleasure to have Kaden, I would say here, but he's here for you, but not for me, unfortunately. But unless it's a pleasure to have Kaden here. So Kaden worked in many different things in the past and recently, and I won't go through all of them. Maybe just a very brief biography. So
you're frozen.
Guys, for his post and his climb for ranks as associate professor. sorry. Am I unfrozen?
Yeah, you're back.
Can you? Oh, I'm back. Okay. I hope you didn't miss too much. Well, so Kaden worked in many different things, and cold atom systems and fundamental quantum bounds, and sort of looking at metrology questions and looking at sort of speed limits, sort of which we'll talk briefly about today as well. So very, very diverse, also connected into numerical works. Also, I have a paper with him a very long time ago as well, related to experiments. So he's very, very diverse and has lots of ideas. And it's really a pleasure to have him here. And I'm sorry I'm not there in person. So without further ado, Kaden, it's all yours.
All right, thank you very much, Zohar. Feel free to just interrupt me, both Zohar and everyone else. I'm really happy to be here. I've never visited Washington University before. Also, actually, I've only driven through St. Louis, and it was during a blizzard, so this is much, much nicer than that. This talk today, I was told it's a bunch of theorists, and so I should make it really technical. So I kind of did. I think given the breadth of how many theorists there are, this could get me into trouble, but I will do my best to get out of trouble. Just ask questions on anything. It's not actually that technical, but we'll see. The ideas here are really deep and far-reaching. I think this idea that locality, it's a principle that holds no matter what field of physics you're in, that if things are interacting with each other, that if things are nearby, they can interact with each other, but if things are far apart, they don't interact with each other. This is something that holds across many, many systems, and of course holds fundamentally in our universe. And so this talk in large part is about exploring the consequences of that. And by operating with such a broad principle, you can draw really broad consequences. So I'm going to start there about some of the consequences, and especially making exact, rigorous results about the consequences of locality. And then this will turn into, if there's time at the end, depending on how much we slow down with questions and things, about locality being consistent with a new type of particle, which people never realized was possible before, called parastatistical particles, or paraparticles for short. So we're all taught there are fermions, there are bosons, then you're done. Maybe if you work with 2D systems, you've heard of anyons. It turns out that's wrong. And I will, if we have time, explain to you how that's wrong and how there are actually other types of particles, maybe potentially fundamental particles, who knows, but certainly emergent particles in condensed matter systems that are neither fermions, bosons, or anyons. And they're consistent with locality. So that's really everything we might talk about today. The take home, if you have to leave right now, is that we can get these broad ideas, broad consequences just from locality. It's a broad assumption, so you get broad consequences. That you can get quantitative rigorous bounds from locality, and that it's worthwhile to improve these quantitative bounds. So the types of people who prove a lot of these bounds are mathematical physicists. And mathematical physicists sometimes have a lot of disdain for improving things quantitatively. So they prove a bound exists, and then they walk away from the problem. And if that bound is 1,000 times too loose for anything you'd like to do with it, they're done, right? And so I want to emphasize that I think in a lot of ways, quantitative improvements to these types of mathematical physics bounds can enable total new applications, and also just have profound consequences for our understanding of matter. And I'll give an example before I start the talk, and then there are these new types of particles. So here's an example of a type of bound that I will sort of outline in this talk, where you take some simple model here. It's like a simplest toy model you can care about in many body physics. You have spin 1/2. They are aligned. They're lined up in a chain a one-dimensional chain. They interact with their nearest neighbors by sigma z, sigma z. So if the spins are the same, they get one interaction. If they're anti-line, you get another. And then you apply a transverse magnetic field to it. In this model, the correlations will spread as a function of time. If I poke a system here, it'll spread as a function of time. And you can go calculate this dynamics on a computer. Actually, it turns out this model is exactly solvable, but that's not important for anything I'm going to say. That's just a coincidence. So you go put this on a computer, or actually to get the infinite size limit, you do have to do that analytically. That's this dashed curve out here. These different curves that stop at various points, orange, green, red, are for different finite size approximations to the system. And what we're doing is we're measuring some magnetization from some fully polarized state as a function of time. And it does something, it doesn't really matter what it's doing, it's saturated to something. And you see that at short times, you get a good approximation from small systems, but then they start to agree. And you get accurate to longer and longer times, the bigger simulation you do. This is anyone who does computational work has probably done something like this. You approximate a big system by a little one. What's frustrating is that it can be very hard to tell if a result like this is converged. Usually the best thing you do is you say, well, I did an L = 9 system, I did an L = 11 system. If you're doing quantum many-body physics, that may be the largest you can go. They agree, and so I guess it's converged. This is not super compelling. So using the types of bounds I'm talking about today, you can actually put rigorous guaranteed bounds on these types of numerical results. And that's what these shaded regions are. The shaded regions stop at some point in time because they just blow up too large that I didn't want to keep plotting it and make the plot messy. But you see it actually works pretty well. What it's saying is the shaded region, the true L = infinity result is guaranteed. You do your L = 5 calculation and combine it with this bound, it's guaranteed to be in that shaded region. And you can see it certainly is. And moreover, you can see that up to this point, it's a very tight, narrow region. It's telling you your results are very good. And where the bound starts to spread and say you might be wrong here is in fact where you start to be wrong. So this gives you a pretty good estimate of where the numerics breaks down. And if you didn't have quantitative bounds, if your results were a factor of 1,000 off in time, you would not be very, these bounds would not be very useful. They might be true, but they're not going to help you actually estimate the error of your algorithm. So I think we were the first people to explicitly point out that you can get these types of error bounds from mathematical physics techniques. And I think this connection of numerical methods with sort of rigorous mathematics is really interesting. There's a lot of low-hanging fruit there. And also we had to improve these sort of bounds to make these, the bounds on the mathematical physics side to make this application work out. Yeah.
In this context, error means deviation from that.
That's exactly what I mean. So the finite size error, which is the difference between the infinite size system and the finite size system. Fundamentally, this is actually proving the thermodynamic limit exists in some sense. It's saying that there is a finite value of this that has to be in this window, even in the limit that L goes to infinity. So that's a sort of, it sounds deeper when you phrase it like that. But at a practical level, this is what it's giving me. It had better be. It's not a prediction, it's a bound. So if it's not too conservative, something has gone wrong and we've screwed up, right? So it does become more and more conservative as L gets larger. Although the way you should probably think about it is what fraction of the time, breakdown time, does it predict? And I'm not sure that fraction is so different than this fraction, right? It's just squeezed way down. So I think that fraction asymptotes to a constant. I don't think it gets worse and worse, but I actually forget. But these are typical system sizes and it works pretty well. It's also going to depend on the details, how well it works on exactly what model you look at. Some might be a little better, some a little worse. We've studied a few. Yeah, so if you are doing any dynamics calculations like this, talk to me and we'll hand you a bound. I should say these bounds come for free. They don't require computational effort. Like whatever effort this L = 5 curve is by far the cheapest took to calculate. Calculating the bound was orders of magnitude cheaper than that. It's not you can even get bounds by hand. You don't have to do deep computation to get the bounds. And before then really, so that was just, so now you could leave and you kind of have the most important salient points of the talk. This is Jiwan Wang. He's just graduated from my group. And he's really been the student that spearheaded almost everything I'm going to talk about today. Basically everything I'm going to talk about today. Absolutely a brilliant student, and you should talk to him if you get the chance. And now real quick, because I do want to advertise other things that my group members have done. I'm not going to tell you about any of this, but I just want you to know that, we're doing other things. Send me an email if you want to talk about it. Our group holds, in collaboration with different experimental groups, a couple world records for ultra cold matter, which is where I spend most of my time, especially working with these Fermi-Hubbard models. This is, you put fermions in lattices. It looks a lot like a condensed matter system, electrons in a lattice. And so we'd like to be able to simulate these systems using ultra cold matter, because ultra cold matter is very tunable. You can image things atom by atom. And so with collaborators, Yoshiro Takahashi's group in Japan, they've actually made the coldest fermions ever in any system. And these fermions have been used to observe what's called SU in quantum magnetism. This is the SU in group like you have in the standard model. And this is just impressive nature physics, very happy. There's some theory of the solid lines, agrees well with the data here. Another experimental collaboration with a group at Princeton has the world record lowest entropy per particle for any fermions and cold atoms. And this is done by using these programmable tweezer arrays. So every one of those green dots is an atom, and they can shape from 1 millisecond to the next millisecond what lattice they want to work with. So this is a totally new capability to our field, or any field, I think, where if right now they want to study this called the Lieb lattice, they can go do measurements, and then half a second from now, they can reconfigure to a triangular lattice, go do many body physics on this lattice, and so on. And you could even, during the time scale of the experiments, move these traps around. It turns out this was enormously experimentally challenging. It was sort of proposed and suggested 8 or 9 years ago, and then people just dropped it because it was thought to be too challenging. There are certain technical issues, but they were able to overcome those. And so I'd love to figure out what are the most exciting things we can do with this system. We're spending quite a bit of time on that. Other stuff we do is new AMO systems. We've introduced this idea of synthetic dimensions for new types of systems where you use, say, internal states of an atom, and you pretend they're lattice sites in an extra dimension of space. And this kind of trivial, silly idea ends up giving exotic new phases of matter. And we have lots of experimental collaborators who are looking into what this leads to. For example, we recently had this paper, this was just single particle physics, but where they could see topological edge states by sort of creating this synthetic dimension system. And then finally, we're doing some things with quantum algorithms and assortment of other things. If any of that sounds interesting to you, yeah, send me an email, or I have some free time after the talk. Let's chat. Yeah. All right. Now it's a good time for a breather after saying all that. We'll go back to the simpler main story. Locality. So since this is supposed to be a broad talk, the different theorists, at least we're starting with the light cone. This looks familiar to probably everybody in the audience. If you operate in our universe, then if an event happens here, all the events that it can affect have to happen inside its light cone. Okay, we all know this. And so if we want to formalize this, what we say is that two operators have to commute if they are outside the light cone. Right? So there's no way that A can respond to B if they're outside the light cone with respect to one another. What's surprising is that, or maybe not surprising, but what's clear and important is that in non-relativistic systems, that's not the only bound, right? So in this room, the information, as I am talking to you, in so much as there is any information coming from me to you, is coming at the speed of sound, not the speed of light. And the speed of sound is a lot slower than the speed of light. So can we understand that, and how can we estimate what that velocity is? Especially for gas in the air, it's not so hard. But for strongly correlated matter, whether it's a neutron star or whether it's a high temperature superconductor, how can we bound how fast that information can propagate? And it's pretty clear there is some bound, but and if you've ever played with this, like you've solved exactly solvable models, they certainly show this. If you take non-interacting particles, my favorite exactly solvable model, they certainly show this even in non-relativistic systems. You can kind of motivate it by looking at perturbation theory, that each time you go to one higher order in perturbation theory, you can move an atom over by one more site. So maybe that convinces you that there's some notion of locality. But how do we really prove that? And so that's really the topic of what are called Lieb-Robinson bounds, which were proved in 1972 by Elliott Lieb and Robinson. So again, as long as you have locality, that's an assumption we're making about our non-relativistic system. Not all non-relativistic systems really satisfy this. If I had a cavity, right, a cavity of light, I put some atoms in it, more or less they talk to each other instantaneously through the cavity, that would not be a local system, right? Or if I had qubits connected to a strip line, they talk to each other more or less instantaneously compared to the other timescales on the system. But by and large, many, probably most of the systems we care about have some idea of locality behind it. And in that case, you can prove that this commutator, which was 0 outside the light cone in the relativistic case, is exponentially decaying outside the light cone in the non-relativistic case. And if you're really careful, you can go figure out how these lambda and s, how the lambda and v are related to the model parameters. So if I give you an Heisenberg model, you can figure out what that says about v. It's proportional to the j that appears in the Heisenberg model, or something like this. So this is really the first and simplest consequence of locality in the dynamics of the system, in the dynamics of these operators. And I should say that this is not just the commutator. What does it mean to say a commutator is less than a number? It's the norm of the commutator. So to think about the norm, this will be used a lot, but all it's doing is saying, if I took an arbitrary quantum state and asked how big is this commutator when I take its expectation value in that quantum state, the absolute maximum it ever is the norm, right? Or it's the largest eigenvalue of the operator. That's what the norm means. So it's the size, the maximum size you could ever get from doing a measurement of that object. Okay, so you go further and further outside the light cone, and this just decays exponentially. It gets very small very quickly.
So what's the assumption? So instead of relativity,
yeah,
you've got some sort of locality.
Yeah.
What say again?
Sure. So the assumption is that you have a collection of objects that interact with each other, and that in the simplest case, objects can only interact if they're inside some ball of each other. So there's some finite radius of interaction, call it R, and every particle can only interact with other particles that are in that radius.
So they can interact instantaneously.
Yeah, but only in a finite way. Or put another way, if you write down a Hamiltonian, you not have chalk in here, it's typically bring out the one corner there. Oh wow, okay. I don't know, maybe I'll turn this for Zohar. So anyway, if you have a Hamiltonian, it could have a sum of one body terms. I'll just write these are terms that sort of act on one particle, plus a sum over pairs of particles, but only if the spacing between Ri minus Rj is less than some threshold epsilon. And then you have some two-body term Hij, which acts on pairs of particles, Ij. So this is the classic Hamiltonian. Actually, you could make this more complicated, not just two-body terms. You could have three-body terms. As long as they're all inside this radius, it would be fine. And then people generalize this. What if you have terms that are non-zero outside this, but you require that it exponentially decays? Actually, this would still be true. So you can generalize it a little bit. A hot topic in our field has actually been generalizing into power law interactions, because in our field, things like dipole interactions, Coulomb interactions, other interactions that come from trapped ions actually have power law decay.
Okay, so this is only really interesting. Well, but since we know the commutator is in fact zero outside the light,
That's right.
where does this bound in?
So it's interesting when there's a huge separation between this light cone, when this v and the speed of light. So for example, in typical materials or in our systems,
Because when it says that the light cone may be out there,
yeah,
exponential suppression sets
in this
way
huge
before
intermediate
you
region. Exactly. Yeah. And in our systems, typical V's might be like millimeter a second, right? Which is not the speed of light. Sorry, when I say light cone in this talk, it's always going to mean whatever this V is, not the real speed of light. So I mean the relative V cone, the relative sound cone or spin cone or whatever. Yeah.
So to calculate this,
No, if you did, then there would be kind of no sense in doing this, because what did you gain? Why you just have the answer in that case? So the point is that this bound can be established just by like almost inspection. I don't have to do any diagonalization of this Hamiltonian. I can just kind of look at the form of this Hamiltonian and tell you from the norms of these individual H and Hij terms what that V is going to be. Yeah, and that's really the key. This is no harder at worst, no harder computation than solving a one particle problem, right? Which is just, if you have insights, it's an n by n matrix, right? And that gives you a bound for the many particle problem, which is a 2 to the n or 5 to the n by 5 to the n problem, right? So you don't have to solve the 5 to the n problem, you just solve the n by n.
Kind of give an implication to how quantum and macroscopic thing can be. So if I have like a big molecule, I'm very intimidated by writing down, describing that the quantum state of that thing. But what this is maybe saying is like one end of the molecule is separable from the other end of the molecule because the time scale, they're essentially local.
Totally. This is perfectly correct intuition. So it's telling you how quantum it can be, or even how correlated it can be. There are many implications of this locality. And so maybe one of the ones that touches closest to what you're saying is one way of measuring, at least for pure states, the amount of non-classicality of two regions is to calculate the entanglement entropy. And these actually give you a bound on entanglement entropy between two regions, how fast it can grow. And so these tell you that the entanglement entropy cannot grow faster than an area times time. So if some area that you're cutting the system into two pieces is a proportionality constant of something that grows linearly in time. You can think of that as there's a constant rate of particles flowing across that bound. So that makes that rigorous. I forget who proved that first, but anyways, it's been proved. In addition to the dynamics, you can actually show that in 1D, in gapped ground states, so there's a deep connection between equilibrium and non-equilibrium physics we'll talk about, at least briefly. So you can actually show in equilibrium, there is a limit to how much entanglement there can be due to these Lieb-Robinson bounds. That non-equilibrium physics has an influence. And there, it's also connected to lots of other things. I mentioned the error bounds, the correlations in a ground state. Again, if you just ask, how does the spin-spin correlation or particle density-density correlation decay as you move particles away from each other? That has to decay exponentially. Quantization of Hall conductance was first rigorously proved, as opposed to sort of hand-wavy flux threading arguments using this sort of technique. So there are lots of implications of this, and exactly this intuition that how long range the quantum correlations can be. That's a great way of thinking about it. Okay, and this was just mentioning one of those, which is called the Lppl principle. It stands for local perturbations perturbed locally. It says if I go and I change my Hamiltonian at one point in space, how much can it affect observables at other points in space? And the answer is not much. If you're outside the light cone, it has to be bounded by the same sort of decaying exponential. And that's going to come back because we've actually proved this for power law systems, which has been a long-standing obstacle. You need new mathematical ideas to do this. Okay. So just real quickly, a lot of people have measured these Lieb-Robinson speeds, seeing how fast correlations spread. And measuring other properties in these very finite size systems. So for example, measuring spin liquid behavior in arrays of Rydberg atoms, or sort of spin dynamics in arrays of molecules, Bose-Hubbard and Fermi-Hubbard spreading. So wouldn't it be great if we could put on those finite size errors on calculations as well as the experiments? So I mentioned that you could put these bounds on calculations, but of course a lot of quantum computers, you've got a finite size quantum computer. How do you bound those? You use the error in those, you use these same techniques. If I do a simulation, if I've built an array of superconducting circuits and I have 50 superconducting circuits doing some many body thing, and I want to know how close is that to an array of 1 million superconducting circuits, this lets you put that bound on. So you don't have to be able to solve the problem to put these bounds on, understand. So there are major issues with prior Lieb-Robinson bounds, which I'm illustrating because we're going to fix all these. First is they were quite loose quantitatively. So in this Ising example, the speed that comes out of the previous techniques was 40 times the actual true speed. At the critical point, it's actually worse at other points. This is one of the places where it's closer. It's also loose in particular limits. Like if I go to this Ising example, but I turn my transverse field way up, I make it very large. In that limit, it turns out it's infinitely loose. The velocity is infinitely slower than what you'd get from the Lieb-Robinson bounds. There's also toric code, a famous example of topological quantum matter. The Lieb-Robinson bounds say this has a finite velocity, but anyone who's solved the toric code actually knows the velocity should be 0 there. So it'd be nice if you had a bound that automatically got that. Or for large spins, so not just spin 1/2, but say you make the spin large, ordinary Lieb-Robinson actually over predicts the velocity there by a factor that's proportional to the square root of the size of the spin. So it just gets worse and worse as you make the spin larger. So we'll fix all those things up, but let me tell you what's wrong and a little bit about how these proofs go. So one way to think about these proofs, there are different ways to go about them, is to think about the Heisenberg picture of operator dynamics, right? So my first term's wrong. This should be an A here. But if I time evolve the operator A, I just get A at time 0 plus IT times the commutator of A with the Hamiltonian plus IT squared, double commutator plus ... And so how this all relates to locality is that if A is on one site, it's only going to not commute with Hamiltonian terms that are nearby. So you can set that commutator to 0 for the terms in H that are not close to the site A. So in this example, the Ising, if A is on the site 0, and I have nearest neighbor interactions, only the Hamiltonian terms that are localized on sites -1, 0, and 1 are going to have any contribution to this commutator. And I can throw all the others away because the commutator will be 0. What about the double commutator? Well, the first commutator gives me an object that's on sites -1, 0, and 1, and taking another commutator expands that by one site. So we localize to sites -2, -1, 0, 1, 2. And so at least order by order, you see this spreads, the radius of this operator spreads. And that's basically what gives rise to the light cone, what I'm calling the light cone. And you can see the problem with this by taking this simple model here. You take a model where you have the sigma z interaction on nearest neighbors, and that's it. You don't do anything else. And my observable is just going to be sigma x. Then my first term is sigma x. My next term is localized to sites -1, 0, and 1. Just like I claimed, you can go compute this pretty straightforwardly. But now, if you believe this is what comes out of the first commutator, and I commute that with the Hamiltonian, here on sites 2 and -2, it actually commutes with these terms. Because this interaction, I have an interaction that looks like sigma 1 times sigma 2, but sigma 1 times sigma 2, the only site I have to worry about is this sigma 1 here, and I'm commuting a sigma z with a sigma z. Okay, so maybe you followed the math, but if not, the point is just that if all you use is locality, you know nothing about the commutation structure. And what's important is not actually the spatial locality, it's the quote algebraic locality. It's when do things not commute. And so certainly if they're far away, that means they commute. But things can commute even if they're not far away. And that's what ordinarily Lieb-Robinson bounds didn't know about and what we put in. So the true answer for this model is that at all times, sigma x of t is actually just localized to 3 sites. It never grows beyond those 3 sites. Ordinary Lieb-Robinson bounds would predict finite velocity that goes off to an infinite number of sites as time increases. And our sorts of bounds, which know about the commutation structure, fix. So how to think about this? I'm actually going to suggest a nice graphical way that I think makes it easy to think about how correlations spread or how this commutation structure takes place. And so if somebody hands you a Hamiltonian, I want to teach you a way to think about that Hamiltonian that in many cases is much more natural than the way we maybe conventionally do. So any Hamiltonian is the sum of terms. There's some ambiguity about how you write as the sum of terms, so pick your favorite. Here I have 3 terms. I have 2 spins. So I have a term that couples spin 1 to spin 2, one that acts on spin 1 only, one that acts on spin 2 only. And what I'm going to do is I'm going to create a graph where each node in the graph is one of these terms. So the H terms are the red triangles, the J term is the blue dot. And I'm going to connect these with a line if the 2 operators don't commute. If they do commute, I don't draw a line. And then I get a structure like this. So J doesn't commute with the 2 H's, but the 2 H's commute with each other. And that's what this is drawing. And now this translates naturally into this kind of perturbative Lieb-Robinson argument that I had mentioned, that you can see the information is going to spread on this graph in a way that corresponds precisely to their spreading when there's a line. Okay, so it's not real space spreading, it's spreading in this abstract space of the operators. And so this is just saying, in words again, write the Hamiltonian as a sum of terms, sum over j, hj, gamma j, and if they don't commute, then I draw a line, and if they do, I don't bother drawing the line. So we go and do this example just to draw some other models so you see what these things look like in more complicated circumstances. So if I do a 1D transverse field, not just two sites, I just kind of make that line I was drawing longer. It goes hj, hj, hj. I can do a 2D model on the square lattice, and it turns out that what you get is something like this. Again, this is not the real space lattice. This is the commutivity lattice. It sort of looks the same, but it's different. The J's live on links between the sites. The red dots correspond to sites. And this is the structure you get. And you can do more complicated things like the Fermi-Hubbard model. It looks, that's the 1D Fermi-Hubbard model. I'll let you think about that on your own. And the main result that summarizes our bounds is that you actually draw this commutivity graph, and you get this set of differential equations on the commutivity graph, where you're just solving a heat, basically a heat equation on the commutivity graph, where the rate of change at each point and on each link is just given by the norms of these operators. The point being that you don't have to go solve the model. You just look at your model, you go figure out what the norms of these individual terms are. That's an easy calculation. If it's all poly matrices, they're all just one, so you don't even have to think about it. And then you just go solve the heat equation on this graph, which is a simple, classical, very tractable problem. And in fact, you can actually, if you don't worry about having the most precisely tight bounds, you can actually just do this analytically. You can solve the heat equation, put a bound on it. It's pretty good.
This diagram here, so you're looking at the commutation relation at the center and mean square at the corner, and so you're looking at how basically
That's right.
space squared between the two.
That's exactly right. Yep. And sometimes you care about observables that aren't in your original Hamiltonian, and then you just tack them onto the graph as an extra note. Like if I had, I don't have any sigma y's in my Ising Hamiltonian, but if I wanted it, I just put a new note here and figure out what it gets with. Okay, so that's it. The happy point is that this corrects all of the problems. What was missing was they didn't understand the commutivity structure. The simple procedure of just solve the heat equation-ish thing on the commutivity graph, it actually solves all of these problems automatically. You get 30% accuracy instead of being a factor of 40 wrong at the critical point. Instead of being infinitely far off for toric code and different limits, you're now, I don't know, you're finite at least. I don't actually remember how far off you are. And you get finite results in a large spin limit that you otherwise wouldn't. And I'll just put one surprising thing here. So this really drives home the point that it's not about spatial locality. Imagine you had a really weird Hamiltonian. You might actually be able to engineer something like this in the cold atom system, but let's not, this is just a theorist's thought experiment. Don't worry too much about how realistic this Hamiltonian is. My first term couples particle or site 1 and site 2 by poly z operators. Then I have something that's a product of 3 poly operators, x, z, z, plus a product of 4, x, x, z, z, and it just keeps going. I keep tacking x's on the front, term by term. This looks terrible. It looks like it's totally non-causal. There's no way you have any locality here. If I perturb here, these higher order terms are just going to connect me to stuff infinitely far away. And it turns out that's totally wrong. So when you go calculate the commutator here, these different terms actually end up commuting. And so even though the terms sort of overlap in space, they don't not commute. So there's no information transport between them. And so this in fact gives you light cones as well. And that's something that I don't think would have been at all obvious. This is of some relevance, although I won't talk to it, actually about the parastatistical models at the end. They actually are somehow equivalent to theories of this form if you do a weird non-local transformation. Okay, so that's the tighter Lieb-Robinson bounds. And now I want to show you an application, what I actually showed you on the first slide, and argue that quantitative is going to be crucial. I'll skip this. This just says finite size errors are important. I think we already made that point. Here's an example. This is from my own research. We were talking about the SUN Hubbard model. There's some correlation function as a function of system size. I plot versus 1 over L. That way the thermodynamic limit should be at the sort of left intercept of the graph here. And you can see you might do a finite size extrapolation by fitting those 4 data points that I had. Those were as large as we could go. But should I fit like I drew there? Or maybe I should fit like the blue line and only take these last 3. And I actually have no idea which is the better fit because I can't do larger system size calculations. So if I could put some rigorous bounds on this, I'd be really happy. Our bounds are for dynamics, not for this situation, so that's an issue, but sure wish I had bounds for that. And people have even shown really bizarre things can happen as a function of L. So you'd like to have these rigorous bounds. The idea of these rigorous bounds is simple. I said that if you poke a system, it can only affect things inside the light cone. So let's think about this finite size error and try to retranslate it in terms of something of poking a system, of perturbing a system. So what I want to know is the difference between my system, which is this finite block here in purple, and the thermodynamic system, which includes all the stuff outside. So what I can do, at least if my initial state is a product state or something simple that doesn't couple the inside and outside, which in many cases for dynamics I care about, that's true, then I can think about at time t equals 0, what I'm doing is compared to the true Hamiltonian, I'm just cutting these bonds that couple the inside and outside. The true Hamiltonian would have the bonds. My Hamiltonian, I'm poking it, I'm perturbing it by cutting those bonds, by turning them off. I'm subtracting them out of the Hamiltonian. And so that immediately gives us this type of bound, Lieb-Robinson bound that I was mentioning, immediately gives us a bound on the finite sizer. Yes?
Is it essential we start in a simple?
It is. That is the biggest limitation. That's right. So this is very, very, very important, and that's why these are still somewhat limited. You know, I think that they apply to a very important class of problems, but not to many of the problems we'd like to understand. If your initial state is correlated, unless you have some bound on that initial error, I can't help it. You have to get a bound on that initial error as well. Now, it does turn out we do have some bounds for ground states, but they're conditioned on a spectral gap. So if you can tell me you definitely have a spectral gap, you know, lowest energy is non-zero for some excitation, then I can put a bound on things for you. And there are cases like in beta ansatz, it's easy to get a spectral gap, but hard to calculate correlations. So you might be able to, for example, take your gap from beta ansatz, do your numerics, and get a rigorous no caveat bound on the error from that, right? But otherwise, you'd have to have a way of establishing that you trust the spectral gap and then building up after that. And there are also some results at finite temperature, but they're for very high temperature, like way, way, way above any phase transitions or anything. So this is where the situation's at. So we proved these finite size error bounds, and we went and plugged in people's previous Lieb-Robinson bounds, and this was the kind of finite size error bound that we got. So here's the L equal infinity again in dashed. The purple is an L equal 21 finite size simulation. And what you see is the error bound is exponentially diverging all the way back here at a time of about 0.5, right? Even though the true calculations go up past 4. So these bounds were just useless for this, for establishing useful bounds on the finite size error. But with our new bound, oops. Oh, there's our new bound. With our new bound, it's this purple curve, which works out to a very reasonable approximation of where the error truly sets in. And so this is a good place to emphasize why I think quantitative bounds are important. If you don't have a quantitative bound, you can't possibly do something like this. And I'll emphasize again that we did not rely on any exact solution. We did not rely on numerics. These bounds can be easily computed for whatever your favorite model is at extremely low computational cost, maybe even by hand analytically.
This doesn't have anything to do with time. There's no velocity probability. It's just a sort of state about how accurately your finite size system will.
That's right, although it's tied to the velocity. And if you go back to this picture, where does your finite size calculation break down? It's when the effect of perturbing the edge can perturb all the way into the observable that you care about, right? So if I want to measure an observable here in the middle, I have to wait until the particles here on the outside or excitations on the outside can propagate into whatever sites that I'm measuring the observables on.
So what I'm imagining is something like, what is the ground?
So
But
these,
that doesn't, you know, you spend as long as you like letting it accept that it's ground state. The question is, how similar is that to?
yeah, and so the answer is we can't answer the question
Oh.
about ground states for this reason, and this
Okay,
is
so-
why we're limited to the dynamics. Now, we do have bounds on ground
Okay,
states.
so could you say again, to me, I think I didn't catch what you were limited.
So we're limited to systems where the initial state has an error that I know. So if I do an initial state where, let's take the simplest case, there's 0 error. It's a product
What do you mean by error?
difference between the L equal infinity and finite L.
But it's like an initial state is something you choose freely. It doesn't, there's no rule that says,
Sure, okay, so if that's, so then you're happy with these sorts of initial state. You could choose an initial state that has correlations between inside and outside. And you can't accommodate that in a finite size system, right? So, but if you're happy choosing states that don't initially have correlations between inside and outside, or where you know the error from ignoring those correlations, then you can proceed to put bounds on what happens after the dynamic evolution.
the kind of state that, is that the kind of state you are talking about, or the kind of state?
If you can ignore those coupling between the inside and outside, then we can put bounds.
What we're putting bounds on is what it evolves into.
That's right. And you see the issue with getting a ground state is a ground state. Maybe you could do, like, if I could do infinite time simulations, I could go adiabatically or something. But you see that the error bounds get really bad at finite time. They're blowing up. And so these bounds are really only good up to some finite time where your excitations can propagate all the way into the center. Now, we do have bounds on ground states, and this is what I've mentioned. If you can guarantee me you have a spectral gap, then there's a different set, like there's a different set of consequences. We have to take a further step. But if you guarantee there's a spectral gap, then you can actually put bounds on ground states.
Bounds also have a light function.
So if you were to ask so if you plotted the size of the system on one axis and time on the other, they would have a light. Absolutely. Oh, sorry, you mean for the ground state?
Yeah.
For the ground state.
Or it just doesn't go.
Yeah, there's no time dependence for the ground state, so there's no real light cone there. It's really just an exponential decay. Now you've asked about finite temperature equilibrium. Maybe beta is something like an imaginary time, but you know, you're really stretching the analogy here. Okay, so that was the improvement in one graph, so you can see how much nicer these bounds are. They've led to new numerical methods. Like if you want to do this in 2D, if I want to calculate a spin observable, how should I shape the region to minimize my error? What I should do is I should make sure the boundary is as far away as possible as whatever as it can be from whatever I'm measuring. So something like a circle, or if you're on a square lattice, it's the Manhattan distance circle, which is a diamond. So these are the optimal clusters predicted by minimizing the error bounds. Calculate that observable. And that's pretty intuitive if you just think you want to put the boundaries as far away as possible. But now what if I want to calculate a 2-point correlation function? What shape should I make the regions? And so you can go do this exercise as well. And now you see you get much funnier shaped regions that minimize the error bound. And I can't guarantee that these are always better, but they certainly make the error bound lower. And in some examples, we can clearly see they're lower. So if you just naively do like an exact diagonalization on this weird disordered system, this is for 10 to 16 site calculations. Already at these short times, there's a lot of disagreement among them. Then you go do these adapted clusters to minimize the error bounds, and you see 10 to 16 sites all agree perfectly, they're perfectly converged, and we have a rigorous error bar. You can't even see it here because it's so narrow at this time, which guarantees the true answer is in that little window. So you see you vastly improved your convergence by adapting your cluster size.
So periodic boundary condition.
Yep.
There is no boundary you want to be far away from. You want to be far away from the reflection of yourself.
That's right. So actually, if you go read our paper, we treat periodic boundaries in there as well. Effectively, the bounds correspond to taking an open system with twice the system size. And this actually works pretty well for predicting how much periodic boundary conditions improve over.
Open system, twice the system. Is that respecting the connection?
That's in 1D.
Right, so I thought it would be two for the, you know, you're on an end for us. So I thought.
I'm not totally sure actually, just because I think you get errors whenever from any direction it propagates into the center. But I'm not sure. I'd have to go look at the formula. Yeah. All right. So let me give you this idea. I mentioned that you can also get equilibrium bounds as well as these non-equilibrium bounds. Let me just give you one example of this connection, which is a new connection that we developed. There's also a very famous connection that Matthew Hastings developed, but it did not suffice for our application, so we had to come up with this new idea. And so this kind of culminates in the first proof of this idea that local perturbations perturb locally. If I have a gap ground state and I poke it, the effect decays exponentially in space. That was proved some time ago for local interactions, but we've proved it for the first time in power law interacting systems. The response decays as a power law. So this is the sort of precise statement of it. If I take the expectation value of some observable in a system H that's perturbed by some Vy, and I take the difference of that with the expectation value of that observable with just H, then this decays like 1 over the distance between my observable I'm measuring and the perturbation V. And this decays like that distance, 1 over that distance to some power. Okay, so that's the main thing that we proved for a gapped ground state. This is just like particle on a mattress. You know, if I have my mattress and I drop a bowling ball on it, it doesn't perturb the mattress infinitely far away. You get a dip that's localized to the mattress. And if you had a mattress that interacted locally, all your springs were connected to their neighbors, then you'd get an exponential decay of all the perturbations. And if you had power law springs that were connected to each other with power law strength, then it would decay like a power law. That's the new thing we proved. Of course, for a mattress, if it's really springs, it's all normal modes, but for nonlinear quantum systems, this also holds. So here's the sort of sketch of the connection between non-equilibrium and equilibrium. This is an incredibly deep thing that, like, I just think it's a very important idea people should know. This is due to Matthew Hastings. And the idea is we all, I think, know this idea of adiabatic evolution. You start from one quantum state, and if you go slowly enough and there's a gap to the other states, then you will reach the other quantum state, the other ground state. You start from one ground state, I end up in the final ground state. I don't go into excited states as long as I go slow enough. And if I go not infinitely slow, but just really slow, that's basically true, but there will be corrections to it. So the remarkable thing is you can get rid of those corrections by evolving under a different Hamiltonian. And this is called the principle of quasi-adiabatic continuity. And this is sort of the precise statement that this ground state that you evolve, that you want to get to, is actually exactly a time evolution from your initial state under some appropriate Hamiltonian. And if your original Hamiltonian is local, this new effective Hamiltonian is quasi-local. It's got exponentially decaying interactions, exponentially decaying in space. And so it turns out that this is really useful for thinking about what does it mean to be a phase of matter. It's really useful for even defining a phase of matter in a precise way. It's really useful for all of these things. This is the conventional connection that lets you go from the non-equilibrium stuff to this LPPL, local perturbations perturbed locally. But when you go to do this for power law interacting systems, any way we know how to generalize this fails. And the reason is that this H effective decays too slowly. It doesn't, the interactions are too long ranged in this effective Hamiltonian for any principle that anyone's ever been able to prove. So you have an interaction that decays like 1 over r to the alpha, and that gives you some effective Hamiltonian that also decays as some power law, but that power law is really, really long ranged. I forget the, you know, it's alpha minus 2 or 2d, but it ends up not giving you any bound for the LPPL, that local perturbations perturbed locally, when alpha is less than 2d. So in 3 dimensions, you could have a 1 over r to the 6 interaction, and that's like the borderline case. You can't possibly prove anything for 1 over r interactions, 1 over r cubed, 1 over r to the 4th. And that's not physical. There should still be a bound. That's an artifact of the mathematical technique. And even for large alpha, it would give loose bounds. So what we came up with was a new approach to get these bounds. This is just a slide saying this. There are a lot of experimental systems, Rydberg atoms, molecules, van der Waals interacting atoms, Coulomb gases, all kinds of things that have power law interaction. So our new bounds fill in, we get bounds for every alpha we should get a bound for. Anytime alpha is greater than d, we think there should be a principle of LPPL, and we were able to prove it in all of those cases. When alpha is greater than 2d, d is the dimension of space, this is a tight bound. We can find systems that saturate this bound, so we know you can't do any better. And for the other cases, we don't know if it's tight or not. We don't know anything that doesn't saturate it, but we also don't really believe it's tight. And we also proved in our paper a bunch of corollaries showing that gapped ground state correlations decay and all these other consequences. So let me just give you a feeling of our new connection between equilibrium and non-equilibrium, and you can more or less see the whole proof. So at least if you remember perturbation theory says that my wave function is the unperturbed wave function plus the perturbing piece divided by the difference in eigenenergies, or for the unperturbed piece, summed over all the excitations. So a different way of writing that same statement is just to write the derivative of the ground state is equal to the same thing, and you write it as an operator instead of writing it a basis. That's all this is. Okay. And you don't have to worry too much about the details. There's some projection operator in the numerator and some difference of the Hamiltonians in the denominator. So now if you want to know how an observable changes as you change some parameter, you can use product rule, right? This is dd lambda of psi sx psi. So you just do product rule on psi sx and psi, and you get these terms. So it's the expectation value and the rate of change in the ground state is the expectation value in the ground state of sx times this funny operator. Okay, and what's interesting is this funny operator is something which we've already seen. And that's what we want to bound. And then we'll be done. If we can bound this thing, we can just use triangle inequality. This difference is just the integral of this derivative. If I can bound the derivative, I just use triangle inequality to put the absolute value inside the integral, and we're done. So it's just a question of, can I bound this weird looking kind of correlator thing? And the answer is, we've actually seen that. So we want to bound the weird looking correlator thing. And that's just rewriting the expression we had. It's the difference of these two terms, setting omega to 0. If I set omega to 0, I get exactly this expression. But if you put the omega in, it's the Fourier transform of this commutator that we did for Lieb-Robinson. So the ground state perturbation theory, how things evolve with lambda, is exactly the same as the omega goes to 0 limit of Lieb-Robinson. Now, I don't think that's actually new to us. I think people appreciated this. Here's the putting it all together. So the gxx, we want to bound this at omega equal to 0. It's the Lieb-Robinson bound. Unfortunately, that bound is infinity. Because what happens is at long enough times, you don't get a bound. We saw this. It's only inside the light cone that you get a bound. So if you wait long enough, you're always probing, it's only outside the light cone that you get a bound. So if you wait long enough, you're always inside the light cone. And all you can do is bound this by a constant maybe. And so if omega goes to 0, this term isn't here, and you have an integral of a constant up to infinite time. This is just infinity. It's not much of a bound. And so this is where so realizing you could actually remedy the situation using some complex analysis was the key insight. You don't really need to follow this, but basically you can think about the analytic structure of this thing we're trying to bound. And even though the best bound we have is infinite at the origin of the complex plane, we have a bound in a circle around the origin. And using something like the maximum modulus principle, this actually lets you get a bound that's better than infinity at the center. So having a bound in a circle in the complex plane actually implies a bound inside that circle. And that can be tighter than the original bound. And it works out here beautifully, and it gives us our result after just sort of elementary triangle inequality type stuff. So that's it. We hope this new connection between equilibrium and non-equilibrium matter is useful for other applications, but we think this LPP alpha power law is a pretty significant initial application, giving us these insights into what are the rules that matter really has to obey. And I should say these quantitative improvements, or in this case, it's really not just a quantitative improvement. These power law bounds are something qualitative. But even these quantitative improvements, I want to advocate for, because in some sense, imagine you've got a magnetic material and someone comes in and says, okay, there exists this quote light cone. I don't think this actually surprises anybody. It's a nice mathematical physics result, but I don't think it's shocking. You expect a light cone. You've done all kinds of approximations. You always get a light cone in any calculation you ever do. But if I can tell you the light cone is less than 2j, where j is some parameter in your model, that might actually, you might actually learn something from that. That might actually surprise you. So in that sense, I would say that the quantitative bound can actually be more insightful or more surprising than just the qualitative results. So that's really the first part of my talk. You know, I had this last section, I was just going to advertise the paraparticles, but I think there are only 5 minutes left in the hour. So I don't know if you want me to spend one slide on that or if I should just stop here and continue to take questions. One slide. Okay, so out of the 30 slides, let me pick which one I want to show you. So there are particles that are not fermions and bosons or anyons. We show they exist. They're not parafermions, which you may have heard of. I'll skip what bosons and fermions are. I'm going to take 2 slides, and I apologize. But here's the first slide. Why are fermions and bosons the only things we have? Well, if you have 2 particles and you exchange the 2 particles, if they're identical, all you can get is a phase factor. Identical means all the observables have to be the same. So multiplying by a phase factor is okay. That doesn't change observables, but doing anything else would screw it up and your observables would change. So now I do this twice. R squared factor between psi x1 x2, psi x1 x2. R squared must be 1. It's the only thing that solves this equation. R has to be plus or minus 1. You're done. You only have fermions and bosons. But wait, there's a loophole, and this loophole bothered people all the way back to Wigner and others. If psi has an index, this R doesn't have to be a number. It could be a matrix. And there are lots of matrices with R squared equal to 1. And this is what a parastatistical particle is. This is what they coined. There's a long, proud history of these things. And you can have an equation that looks like this. So because of time, I won't tell you about it. For a long time, people thought this was impossible. Even today, I think if you go ask anyone, they'll tell you it's impossible. They might even tell you there's a no-go theorem that's based on weird C-star algebra type arguments that I don't understand, but I can tell you that theorem doesn't actually apply to everything. Because we've constructed exactly solvable models that have paraparticles as the excitations, and we can prove they're not equivalent to fermions or bosons. So you can either write down sort of at a fundamental level, you can write down a quantum field theory, and you can show that it's compatible with relativity, with there's no anomaly when you take the continuum limit, all of these things. You can show that that theory is perfectly well defined, perfectly local, perfectly compatible with locality, and get a paraparticle theory. Of course, I don't know if nature gives us any paraparticles. You know, as far as I know, probably electrons are not paraparticles. Maybe they are. What do I know? But what we've also shown is that there are spin models, just spin 1 models, like you get, you know, in a magnet. There are simple spin 1 models of 2-body interactions whose fundamental excitations are non-interacting paraparticles. And again, this is essentially a proof that at least as emergent quasi-particles, you can have this type of excitation. And so now experimentalists should go search for these things and go find them. And I have collaborators in cold atoms that are doing exactly this. So let me just put up my conclusions. Let me stop there. I hope I've convinced you that, you know, locality is important, and without getting into details of specific models, you can get lots of rigorous, broadly applicable results from locality. The things inform your errors in simulations, structure of ground states, using deep connections between equilibrium and non-equilibrium physics. You can treat both. Hope I've espoused a little bit the idea that quantitative improvements in these things can be interesting. I've at least advertised that there's a new type of particle we should all be paying attention to, and I can tell you all about that if anyone cares. So thank you very much. So they're not fermions or bosons. They're something different. Depending on what you mean by statistics, if you mean what happens when you exchange, they have this weird matrix that governs how they exchange. If by statistics you mean like the occupation numbers, like do I get a Fermi function or a Bose function? This is the answer. There are actually infinitely many types of paraparticles because there are lots of matrices you can pick. But here are a couple of simple examples. Let's just look at this column. So you could have a vacuum, and then you could have M types of paraparticles. So just like with fermions, you'd have spin up and spin down. Here, maybe you have a para spin up, para spin down, not ordinary spin, but two possible states. So what are the possible levels you could have? That you have this generalized exclusion statistics where you can have vacuum. You can have, if I have one particle, I can have two types of particles. But unlike ordinary fermions, I can never put two particles. There are no two particle states here. That's the generalized exclusion. So even though they have a sort of quote spin, there are no two particle states. And you can show that this is a consistent type of non-interacting theory that you can calculate everything in. That's the surprising part. Of course, you can have systems like this. It's just not at all clear they correspond to any non-interacting theory. In fact, these do, and their statistics are just given by this function here. So the average number of paraparticles in a mode with energy epsilon is given by this expression. M is the number of levels here, so it would be 2 in this example. So it would be 2x. X is e to the minus beta epsilon minus u. So this is m times x divided by 1 plus m times x. For fermions, m will just be 1. So this is a very simple modification of fermions, but it does not correspond to just say taking 2 independent sets of fermions. That would square x plus 1 over x. Whereas this cannot be written as a sum of things that just square or take powers of the Fermi function. So this is no combination of non-interacting fermions. So the main thing about locality here is it's actually, if you don't care about locality, you'd think there are tons and tons of solutions for these paraparticles. But what you'd quickly find is you'd write down your Hamiltonians and you would be able to have non-local operators. So if I literally just defined the sort of, so I could do this in second quantization, right? So I had this these operators that tell me what to do under exchange. I could use the same sort of thing for a psi dagger psi dagger. I could say psi dagger 1, psi dagger 2 is some matrix acting on psi dagger 2, psi dagger 1. That gives me the commutation relationship. If I do that, then you'd say, fine, I know how to write non-interacting theories. They're psi dagger psi, just sums of psi dagger psi. And in fact, that is a non-interacting theory. You can go calculate everything about it, just like any non-interacting theory. But it turns out that almost always that does not obey causality. So it's only when you carefully incorporate a causality locality, I'm using these simultaneously, to mean the same thing. So only when you carefully choose the structure of operators you're allowed to put in your theory, do you recover the locality. And you do this by ensuring that operators in different points of space commute with each other, just like we saw in the Lieb-Robinson. So the classes of Hamiltonians you're allowed to build out of the operators is restricted by locality very severely. And beyond just saying they have to be at the same time. It's not enough to just write down that the size have to be close to each other. You also have to treat very carefully that extra index I added. That has to appear in a specific way in Hamilton. Zohar, are we done?
I mean, it's fascinating stuff. So yeah, it's really nice. I'm just curious, what does the model actually, some of the models that you actually have look like give rise to that?
For the paraparticles?
Exactly.
Yeah, okay, so I have a slide on that. So this is a sort of very abstract looking model. Here, if you look on the left, this is a 1D spin chain. The simplest example I know is each spin has 3 states. And then it's a sum. It looks very much like an XXY model or XY model, S plus S minus plus S minus S plus, but it's not quite the usual S plus and S minus. Instead, it's an operator that takes you from the spin 0 state to the +1 state, but then you have to be very careful about what it does when it brings you back. Okay, and so I can show you the equations for this, but it is just a spin 1 model. It's not particularly exotic. And how we actually got onto this, you know, is I don't know anything about any of this fancy stuff, but if you put Rydberg atoms in traps and line them up next to each other, it's exactly the Hamiltonian that you get by default. You don't do any engineering, you just build your system. I have a bunch of collaborators doing this, and it turns out the exact solution of their model gives rise to these paraparticles. Oh, that's a great question. So, so non-abelian anyons are in 2 dimensions, actually have all the same stuff here. The difference, and so these are actually a special case of non-abelian anyons. Non-abelian anyons have to satisfy something called the Young-Baxter equation that describes how they braid. These satisfy Young-Baxter plus an additional condition, which is r squared is equal to 1. The issue is that if you extend to 3 dimensions, there's no way to extend a non-abelian anion in general to 3 dimensions. We don't know of any. That's exactly right. That's right. And so the point is that up until now, people thought there would be nothing non-trivial in higher dimensions because the braid group disappears. But in fact, even the permutation group representations can have non-trivial higher dimensional representations. And that's exactly what we showed. And then there's a small little technical thing about you have to be careful whether those are equivalent to combinations of lower dimensional representations. And if you care, that's a longer discussion. But we definitely know in the exactly solvable model they're not. Whether we can do that in 3D is still an open question.
Should I corresponding to local and indistinguishable?
That's right. And that's exactly the criterion when I said you have to be careful about the terms you put in your Hamiltonian. You have the only terms you're allowed to put in the Hamiltonian if you want to preserve causality can't distinguish between the different indices. So if you have a paraspin up and paraspin down, you can't have an operator that just acts on paraspin up. You have to sum that internal index. And that's enough to guarantee causality. So very good intuition. That's exactly right.
I maybe recall have discussed something about that as emergent superconductor.
There are certainly non-abelian anyons, but I don't know of any systems that would extend to higher. I don't know. Not that I know of. There are certainly exotic line defects. You can have line defects that commute in weird ways with point particles, but I don't know any that have point excitations that have a non-fermionic proposal. If you do, please let me know. But, yeah, I don't know.
So please ask all the questions that you could ask.
Yeah.
Thank you so much again.
Thanks.
Thank you very much.
Thanks, Zohar. Where are you actually at, Zohar?
I'm in Oxford.
Oxford. Oh, okay. Who are you visiting? Thank you.
Shivaji.
Oh, nice. How's he enjoying the new home?
I think he likes it.
I'm sure. Is Sid also there? Sid Parameswaran, is he also
It
at
is very exciting.
Yeah.
Yes.
No. Nice.
Yeah, exactly. These are really nice results. I mean, I have to digest them.
Yeah,
It's very
it's not very simple stuff, but I think that, you know, it's manageable. It's not too long involved calculations.
I mean, we never thought about. I mean, we thought about things which are related to that because of bond algebra. But what you did with combining the Lieb-Robinson is really beautiful.
That's right. I mean, so your bond algebra ideas were extremely useful. You know, I should do a better job of citing a lot of people in this talk, which I didn't, but your bond algebra ideas were really inspirational. And even for the parastatistics model, like the way that we realized the parastatistics are equivalent to this spin model was actually through bond algebra type idea.
I see.
Also, some other things that you've done with, I think you've worked with these generalized Jordan-Wigner transforms and stuff. There are some connections here.
After just, I mean, yeah, I mean, this is really fascinating stuff.
So actually, I didn't mention, so it turns out this is kind of the connection. If you see this equation here, the psi plus equals blah, blah, blah.
Yeah.
The point is to go from the spins to the paraparticles. It's a Jordan-Wigner transform, but instead of -1 to the density, you do a matrix product operator that's carefully chosen.
I see. I see.
And as far as I know, it's a very simple idea to use an MPO to do Jordan-Wigner, but I don't know anyone who's done it. And the reason may be that anything you can do with an MPO, if you want to map it to non-interacting particles, I think the only new things you get are paraparticles. I don't think you get anything new for mapping to fermions and bosons. So people may have just not realized that you got solvable models because they got a paraparticle model and didn't realize that it was non-interacting particles.
Right.
So there's some people here in the room too. Nice to meet you in person. Oh yeah.
Thank you so much.
My name is Joe Wong.
Of course, yeah, we're Facebook friends.
Oh, really? Thanks. Actually, I'm a very good friend with Nature Way.
Oh, okay.
So I'm very excited to see you.
Did you were you undergraduate classmates?
Yeah.
Okay, Soccer, I need to leave.
Okay. Okay. See.
Really excited.
I cannot ask a question, doesn't matter. In any case,
Thank you.
I am not going to
Who are you working with?
give information. See you, Soccer. Bye-bye.
Bye.
No. Actually, I sent you in March, and
Did I respond?
yes, of course. Thanks.
Sorry.
And it's like at that time I was applying to.
Oh, so you're first year.
Yes.
You're just getting started.
Yeah.
I see, yeah.
So it's so interesting.
Yeah.
So can I take a picture with
Oh,
you?
of course.
Just posted it on
Oh my goodness.
with
Yeah.
Twitter or something.
I think that's fun. Yeah.
Okay, thanks.
No, I'm like a celebrity. I love it.
Okay.
Sure.
Actually, also moving on.
Oh, okay.
And I'll mention you on that.
That's fine. Yeah.
Okay, thanks so much.
There are no secrets in the talking.
I'm Mark also. I'll do this. if you don't mind. So yeah, so I just wanted to, very interesting. I just wanted to make a rather maybe pedantic point about the very first thing you said about how the fact that someone can't talk to something outside the slide cone is saying the operators don't commute. I think they're not quite the same thing. And the Einstein-Podolsky-Rosen thing is an example of that, where you have a theory, quantum mechanics, but they commute outside the light cone, but you can still get correlations between space-like separated things that aren't due to anything in their past life.
So you can get measure. You can get certainly the quantum states you get.
What's different? I'm talking about correlation, about measured correlations. I guess I'm talking about correlations between outcomes of experiments.
That's right. Of course, this can't be used to transmit information.
It can't be used to transmit information, right? But there's all this sort of slight sort of weirdness that there's these sort of these ideas of causality and locality that are all kind of almost the same, but at the edges there are places where things that one covers, the other one doesn't quite cover.
It's a very good point to be careful.
And
Where I think it's clear is like, so if you go into this sort of, if I perturb the system and ask about it.
Yes, that's fine, yes. Because you can control the perturbations, so you could send a message that way. But as a blanket statement, it's not quite true to say that the absence of correlation is outside the light cone is the same thing
That's
as
absolutely, you're right.
commuting operators. It's loosely true, and I don't think most people sweat the difference, but this is one place where it becomes a huge thing that everyone talks about forever.
Yeah, well, of course there are, people. A lot of these are practical issues.
I hadn't heard of that. So
Yeah.
that's
So you can actually on scrambling and all that stuff. So there's a whole thing about like
Where scrambled just means it gets sort of stored in an obfuscated type of way that you can't easily.
So local, like a local operator gets encoded into the very knowledge block. This balance on my whole also have now and it's sort of bound on how fast it's scrambled. Yeah. But I it's all been very fun to me.
Yes, yes. And so I heard of Parastatistical, and I thought that what I heard was that they were some sort of non-abelian matrix variant, but I thought I'd heard that going back years and years. But so what you're sort of saying is new. Is which aspect is new?
So there's a famous theorem that's in Parastatistical. So back in the 70s, down Parastatistical, very special case of what I was doing. And people realized this is actually a combination. And then three mathematical physicists, the DHR team.
Okay.
It's very fancy and don't really understand that. Actually, the right and then so this.
In other words, anything that you claim is not that is reducible to something. Okay.
Exactly. And you could even thought initially, of course, maybe try to shoot.
Yes, yes. I mean, I think that's partly right.
Exactly. But the point, and you can try it that way.
Yes, there's an idea of how to get out of how to explain the fact that yeah, you have these things. Yeah, you think these hadrons should. Right. Yeah.
Precisely.
What you end up explaining in terms of a hidden degree of freedom of color, yes. And symmetrized, they had this other, okay, maybe they're parallel.
But they end up being equivalent, so why not just turn around and go down with that? And so this is everyone believes this, based on this, that seems to have the issue is, we didn't know something's wrong, not wrong, yes, it's correct. And I know things are no, I mean, right. And this term applies to 2D, so what? And you can correct actually, if your excitation circle system, that's important. When you look at excitation, look for excitation, by look for it, look with some of this very applies some yeah, local excitation. But this is actually very restrictive. So, my think about two models, non-local with an axis.
Right.
And this is, I'm probably not the exact so this is a much more educational. We don't know we have our terms. Depending on how much you do about fundamental universe, like something about anybody would say it's fundamental work. So it's a well-defined term, it just doesn't actually rule out whatever it is.
Okay, but presumably,
yeah.
If you believe in relativity and stuff, then excitations have to be local at some level, right? Like I can't have something that consists of me doing something here and something behind the moon less than half a second.
The issue is how locally, because I think the important notion is algebraic. If I have access to a certain set of operators, I can't tell if secretly on some underlying degrees of freedom, it's doing very non-local things.
Right.
If I don't have access. So if those are like a Planck link, like a Planck link, probably I wouldn't have a clue if it's actually creating these things if I don't have a so if the allowance of operators was just the Char index ignorant to operators, it could all be non-local excitations without me ever knowing. It's like if you had a theory that let you, so imagine you had these magnets, but imagine the only operators you could measure were involved in the string. So.
Quickly, maybe because I'm being picked up, I don't have a parking code with this semester. So I'm Alex.
Sorry.
I'm so sorry I didn't make it onto the schedule. I wasn't sure I would be able to come out to coordinate. And I'm basically in the process of leaving the country because I'm.
Are you going to Germany? Or are you the one I heard? I heard, yeah,
Yes,
okay.
yes.
What, LMU or?
Yeah, actually TU.
Oh, okay.
So, but I'm very glad I could at least make the talk. In fact, it's the only talk I'm coming to this whole
I'm very
semester,
privileged.
this whole
Okay.
year probably.
Yeah.
And I
So we
really
won't
enjoyed
see you again until
Yeah,
this
that-
time in 2020. Are you going to come back at the
it.
beginning of the summer or?
Times are very uncertain,
Well, right.
but I hope, I guess that's the plan.
Yeah.
I will be.
So who's your host at?
From.
Oh, okay, yeah. Tell him I said hello. I
will.
don't know if he actually remembers, but yeah, he probably, we've interacted with that. Yeah, well, thanks for making the time to come, and so when you leave the Germany.
I'm leaving on.
Oh,
Not Monday, the holiday. In Germany,
oh, okay.
if I remember correctly.
Actually, I'm a student coming to my group from Germany, from LMU for 6 months. He's a visit from, do you know, Fabian Brust? Okay, he's excellent, young, just started there.
Oh,
Works a lot on these other model quantum gas microscope experiments.
well, great to meet you.
Thanks, yeah, nice meeting you.
You, Mark.
See you in. Are you staying in Garking or? Brighton or
Yes,
something
yes,
like that?
that's at least for 3 months. In fact, they have this on-campus hotel similar to the night center. That's where I'm going to be for 3 months, and then some family will go on. I'm still working.
It's a very nice. Well, you.
They have a cool subway, right? Like,
Oh,
they have all the
right,
physics
right,
stuff in the
right,
subway. I
yes.
think that's great.
Yeah, I'm not going to have a call at least for those 3 months.
Yeah.
Are you German or? Practice your German.
Reawaken it.
It's sort of necessary. Yeah.
And the question, have you started to dream in English yet? Because I know after people live in the US a
I
lot.
really don't know the answer to that, but I think I observed that it is mixed.
Yeah,
I'm not 100% sure.
you just dream in pictures. That's fine.
Well, you'll start learning.
I think
Bavarian. You'll start becoming Bayerish.
yeah, that too. I've lived in that.
So it's just in time for Oktoberfest. Just in time for Oktoberfest.
Yeah, well, it's the Oktoberfest takes place at the end of September. So I'll skip that. I mean, my thought is that they will just read the next variant there. But it turns out I just recovered, so it doesn't matter. I could have.
Oh, you
gone
just
with-
had COVID?
I just had COVID. I could have gone with it.
Yeah, I've been through, vaccinated, boosted, got it, yeah. Actually, I was at an Aspen workshop this summer, and out of like 40 participants, I think 10 people got it while we were in Aspen.
Yeah,
I was in
great
Aspen, but I was in
story.
Aspen at the very beginning of the summer, like first week in June or something. So I think that was before it went into cold.
This was July.
Right, everyone.
Yep, see you.
Yeah, see you.
It's a good time.
Thank
So
you.
let me just real quickly draw the
Yes.
point I was making. So if you have a name. And the only operators you have access to, imagine that just as a rule of the game, for whatever reason. I said you could only measure
Nearest,
like this.
nearest neighbors.
Yeah, so let's just say that again, these spin degrees of freedom are some plot point or whatever, it's something very microscopic.
Okay.
Let's just say this was the operator. All you ever knew was there was some operator OI. I secretly know what's going on underneath, and I know it's okay. But if this is all you can measure, you'll never see that this is a non-local object, right? The
Right.
only thing is if I were to is it's
Right.
looks like this. And this is sort of what's going on in these theories. That sure, there is some underlying Hilbert space when you describe these things, where the excitations are not local. But if for whatever reason you didn't have access to all the operators of the theory, you would never be able to tell.
But so that theorem you said, so doesn't that theorem apply to the set of, so the set of operators in which it looks, in terms of which it looks local, or is just somehow the existence of this?
No, the existence of the underlying micro.
That's enough
So
to
it's really
take
talking
it
about
outside the scope of the
That's
theory.
right. It's really talks about the structure of the states, not about the structure of the operators. In my
In other words,
frame,
all
which is-
possible, all possible, all definable operators as distinct from all, by whatever criterion, implementable operators.
Exactly.
Okay.
So if you, and so this, in the algebraic quantum field theory, these are called the quote local operators. So it's a subset of all the possible things you might define on your Hilbert space, and that's sort of the operators that you're allowed to play with in quantum. So, you know, I don't know, maybe this is all rubbish, and of course, getting this okay with relativity, you have to have a really fine grained matter, I'm sure. So I'm not taking it too seriously, but still, you know, I think just conceptually, it helps clarify that you can have some set of observables that you never know these objects are local, and this is how it's certain.
Now, so in a, presumably you'll think that condensed matter system does ultimately have a set of local things that it's very root, you know. So
In our exactly solvable model, it's very similar to this. So you have a bunch of spins, and the paraparticles are domain wall.
Okay.
Yeah,
So
that's
it's
not quite as clean. It's actually some weird matrix product domain wall, but
yeah, I'm just trying to think.
so this is what my experimental friends are doing with the Rydberg atoms. We're actually trying to make two of these excitations, scatter them off each other, and see.
I see. So it will show up in the scattering cross section or something, or some phase difference.
Hopefully in the cross sections, but it's actually, again, it is something we're working out, and I can't give you a precise.
It seemed like it would just show up in the you were talking about the thermal populations, right? Wouldn't that be a rather easy way of
You would see
seeing it?
cold atoms getting things to thermalize, so
okay, yes.
getting them to thermalize at low temperatures is even less.
Yeah.
It depends on the system, but especially for the kinds of systems we're thinking about here, that's maybe not the easiest.
I see.
But it's definitely.
Normally one thinks of, you know, just getting stuff to sort of heat up and go thermo is normally just what it does, even if you don't force it. But in this case,
I was trying to talk to your colleague Chong Yu, is that his name? Chong Zhu, yeah, exactly.
experimentalist does diamond.
Exactly. So diamond nitrogen basically are spin one systems.
Uh-huh.
They have dipole-dipole interactions that are exactly the same as this Rydberg system, and the level spaces are basically the same. And so I said, you could do this in equilibrium. Why don't you do it? He said, oh, actually, they don't equilibrate here.
Oh, really?
Okay, but yeah, that would be very good. Yeah, nice meeting you.
Very nice to meet you. So I was sort of a part student of Frank Wilczek back in the long ago times. So yeah, we heard a lot about anyons and brave.
I'm sure you did.
And whatever those Baxter things.
No chance you overlap with Vincent Lewis there. You know that?
His name sounds familiar.
Okay, he was a student of Frank Wilczek as
He
well.
must have been a little after.
Okay.
Well, I'm really Sidney Coleman's student, but I wrote most of my graduate student papers with Frank.
Yeah.
And that was in the late 80s.
Yeah, I'm not sure when it's
Vincent, man.
out that time. Plus or minus 5 or 10.
During Frank's anyons, sort of while he was learning to do.
Yeah, well, certainly we're indebted to him. Yeah, thank you. See you around.